So in section 1, we talked a lot about intermolecular forces. Reminder, an intermolecular force is simply an attraction between two molecules, and the stronger those intermolecular forces are, the more we can predict properties such as higher melting points, higher boiling points, etc. We also talked how about solid states have strong intermolecular forces. In the liquid state, the intermolecular forces are still there, they're just a little weaker. And finally, the gas phase has no intermolecular forces. That's why the particles are able to freely move around. So now that we have an idea and understanding about all of that, we can now get into section 2, which is going to briefly talk about several different properties of liquids that tie back to that idea of intermolecular forces. First of all is surface tension. You're probably familiar with surface tension, right? You see a bug or a leaf floating on the surface of the liquid, and it doesn't quite penetrate the surface of the liquid. It's able to float. Well, surface tension is actually directly correlated to intermolecular forces. Surface tension is actually defined as the amount of energy needed to stretch out the liquid. Well, what does that mean in terms of intermolecular forces? What we find is that the higher the intermolecular forces for the particular liquid, that means more energy is needed, and therefore that's going to result in a higher surface tension. So a pool of liquid, such as water, for example, would probably have a lower surface tension than maybe a pool of syrup. Both are liquids, but you could probably predict that syrup would have a higher surface tension. And that's because it has higher intermolecular forces due to its actual atomic structure. Now, this gets into a conversation about different terms such as cohesive, right? So when we talk about cohesive forces or cohesion, we're talking about the attraction between like molecules. So if you think about a molecule, let's say here, and it's obviously surrounded by molecules of itself around, the forces that are in between there, yes, they're intermolecular forces, but we would say those are cohesive forces or cohesion forces. Another term to be aware of that's not on the slide, but you should add it to your notes, is what's called adhesion, okay, or adhesive forces. This is going to be the attraction between different particles. So, for example, if you think about a test tube that's made of glass, right? We kind of take for granted that they're actually molecules that make up glass, right? And you've got water inside here. You may have noticed that there's a meniscus. The water seems to be pulled up or attracted to the glass. Well, that's because there is an adhesive force, which is still intermolecular, but there's an adhesive force between the glass particles and the water particles. So those are some terms to be aware of. All right, so that's surface tension. What about viscosity? Viscosity is defined as the measure of resistance to flow. In other words, the higher the viscosity, the more resistance to flow. It won't flow easily. So substances that have high viscosity are things like ketchup, chocolate syrup, fondue, toothpaste. Kind of weird, right? But technically, those are liquidy, but they don't flow very easily, do they? Let's contrast that to things that are low viscosity, such as water, acetone, motor oil, any other ionic liquid, but you get the idea. Those flow a lot easier, and that's because it's low viscosity. But how does that relate to intermolecular forces? Well, the higher or stronger intermolecular forces would be over here with the high viscosity. Why are these substances not going to flow easily? Because as you try to pour them out, those particles are all sticking to each other because of the high intermolecular forces. They don't want to flow easily. Versus over here to the left, this is where you're going to have low intermolecular forces. And that's why these substances can flow a lot easier. Now, you can actually decrease intermolecular forces. You can decrease viscosity. You can make a substance flow easier by increasing temperature. Because what increasing temperature is going to do is it's going to make those particles move faster. And if they move faster, the particles are able to overcome the intermolecular forces. The intermolecular forces will be weakened. And so you may actually have experienced this. Hopefully everyone out there eats breakfast the right way. And that is, you don't put cold syrup on your pancakes, right? You want to make sure that syrup is at least at room temperature. If not, the best way is to put the syrup in the microwave for about 10 seconds and warm it up. When you do that, the syrup flows a lot easier. Well, what you're actually doing is you're supplying enough energy to weaken those intermolecular forces, and therefore that will decrease the viscosity. So as a reminder, high intermolecular forces, viscosity is high. And if you want to weaken them, simply just increase your temperature. All right, the last one we need to talk about is vapor pressure. And this is actually a new concept to many of you. What is vapor pressure? Well, when you hear vapor, I want you to think of the gas state. Okay? It's the gas state of any substance that was normally solid or liquid. And then pressure is a new one that you might not be familiar with. Every time a particle moves around, think about the particles that are in the air right now. There's a lot of particles that are in the air that we don't see, but they are there. And think about it. There's a ton of them. There's billions and billions upon billions of them all around you. And they're all bouncing off you, bouncing off your head, bouncing off your hand, bouncing off your chest. They're bouncing off everywhere, right? Every time a particle bounces off of something, it exerts a pressure. So if this was a wall, and this was a particle, and it hits the wall and bounces off, that right there is a pressure. Now, one particle, that's not a lot, but if you think about a lot of particles doing that, that adds up. So now that we have an idea of what vapor is and what pressure is, let's put them together. When compounds are in the liquid state, let's just think about a glass of water as an example. There are always some molecules that will escape into the gas phase due to evaporation. And so if you were to take a look at the picture, most of your water particles are still down here in the liquid form, so they're being held together by intermolecular forces. But some water particles were actually able to escape into the gas phase. They've overcome the intermolecular forces and are able to escape into the gas phase. Now think about it. These particles that are now in the gas phase can move about, and what they do is they bounce off the sides of the container, okay, and they exert pressures. Now, what would increase the pressure up here? Well, more water particles, right? If there were more water particles that were able to escape into the gas phase, that would mean a higher pressure. Well, what is going to create more particles in the gas phase? What would allow more particles to escape into the gas phase? More particles would be able to escape if you had very low intermolecular forces in the liquid phase, right? Because if they were weaker, more particles would be able to escape, and therefore higher vapor pressure. So I know that might have been a lot, so let's recap that. Molecules are going to exert a pressure known as vapor pressure when they are in the gas phase. The more molecules that are able to escape, the higher the vapor pressure. And we talked about if the intermolecular forces are weaker in the liquid, more molecules will be able to escape. And therefore, tying it all together, weaker intermolecular forces in the liquid mean higher vapor pressure. So let's look at an example, okay? Let's look at example 5. This is a great question. It might not seem that great to you, but this is really testing your knowledge of intermolecular forces and vapor pressure. So in example 5, it says, if figure 1, which is right here, represents the vapor pressure of diethyl ether, don't get so concerned about that. Just keep going. At 25 degrees Celsius, which figure would represent the vapor pressure of ethanol, which is given there, at the same temperature? So it's basically saying, hey, same temperature, so temperature is not a concern here. You're essentially comparing two compounds, diethyl ether and ethanol. All right? You want to see which one of figure 2, 3, or 4 would represent ethanol. Okay, so you've got diethyl ether that's right here. Now, figure 2 is the exact same as figure 1. So what that would represent is, hey, these two molecules must have the same strength of intermolecular forces, right? That's what that means. In number 3, you can see that there are more particles that were able to escape in the gas phase, which means the intermolecular forces are really weak. And in figure 4, there's very few that were able to escape, which means the intermolecular forces are very strong. So keep that in mind. That's essentially what we're trying to figure out. Well, we know both of these, okay, are going to experience London dispersion forces, right? So we got that. If we take a look at ethanol, ethanol is going to experience hydrogen bonding, right? What about diethyl ether? Look at structurally how it's put together. Is this one going to experience hydrogen bonding? It's not. Okay, think about how it's bonded. You've got your CH3 plus your CH2 plus your O, then your CH2 plus your CH3. You see how no hydrogens would be bonded to oxygen? So because of that, ethanol is stronger. The intermolecular forces for ethanol are stronger, which means, are they going to be able to release as many gas particles? No. And so the one that would represent ethanol is going to be this one right here. The intermolecular forces are stronger down here, which means it would release fewer particles in the gas phase. All right, we're almost done with this section here for section 2. We just want to talk about one last thing, which is boiling point. We've actually been talking about boiling point for quite a while. The boiling point is the temperature at which something boils. What is boiling? What actually is the process of boiling? Well, the definition of boiling is it's when the vapor pressure is equal to the external pressure. So if you think about you put a pot of water on the stove and you turn it on, right? Well, if you've got this pot of water, okay, on the stove, there may be like a few particles that are able to escape into the gas phase, right? But if you think about all the particles that are in the room, the atmospheric or external pressure, it's a lot more, right? So if you think about, wow, this external pressure is a lot stronger than, I'm choosing different colors here, is a lot stronger than boop, the pressure from the particles that are able to escape, right? But if you think about as time goes on, the amount of particles that are going to be escaping into the gas phase are going to keep increasing more and more and more, because as you keep applying heat, which I'm going to be a terrible drawer here, but heat, fire, okay, that's going to supply enough energy to start to allow more particles to escape to the gas phase. And so you'd end up seeing the vapor pressure increase more and more and more, till finally, here's the definition of boiling. The boiling will actually begin when the external pressure is equal to the vapor pressure. That's really tiny, but that's the area of boiling where it's the same. And obviously, as your vapor pressure gets higher and higher, that's where you start to see particles actually leaving, and the water level starts to go lower and lower. So what is boiling? Boiling actually is when the vapor pressure and the external pressure equal. Now, external pressure is different on all points of the earth. You could be in a deep valley. You could be on the top of a very high mountain. So that's why substances like, for example, water will actually boil at different temperatures or different atmospheric conditions, because the external pressure is different, right? So when we say water boils, you may have heard this before, hopefully. They say water boils at 100 degrees Celsius. Well, that actually is variable depending on where you're at. But why do they say, when they say water boils at 100 degrees Celsius, or that the boiling point for water is 100 degrees Celsius, what they're really saying is the normal boiling point. And normal actually has a definition. When we say normal, we're saying the pressure is 1 atmosphere of pressure, which is like your basic pressure in a room. And the temperature is 0 degrees Celsius. Because what we're going to realize in this topic is that things vary a lot with conditions of temperature and pressure. So it's not enough to just say, oh, water boils at 100 degrees Celsius. Well, it actually depends on where you're at in the world and what the conditions are. So when we say that, when we report that water's boiling point is 100 degrees Celsius, what we're really saying is its normal boiling point is 100 degrees Celsius. And remember, normal means 0 degrees Celsius and 1 atmosphere of pressure. So that wraps up section 2. In section 3, we're going to take a little look at solids now.